For this video, we're going to talk about real numbers and the number line. First thing we're going to discuss is the square root. Definition of the square root: a number A is a square root of a number B if A squared equals B, or A to the second power. So what we're saying is any number, let's say 7 to the second power is equal to 49, so we say that 7 is a square root of 49. Because 7 times 7 gives you 49. Now we indicate that using a little symbol called the radical symbol, like this. And we can put the number 49 here, like that. And then we just draw a bar to represent what part of the value, if there's more than one number, for example, do we want to take the square root of, and we would say that this would equal 7. This number under here has a name, it's called the radicand. And this, of course, is called the radical symbol. This whole thing makes up a radical. So the square root of 49 equals 7. Another example might be square root of 36. And we think to ourselves, what squared, or what to the second power, or what times itself gives you 36? And that would be just 6. Here's a couple other examples. Square root of 81. So we're thinking what times itself gives you 81, and that would just be 9. 9 times 9 gives you 81, therefore 9 would be the square root of 81. We have an example like this where it's a fraction. You can actually rewrite that as 2 square roots, the square root of 9 over the square root of 16. If you want, you can think of what fraction times itself gives you 9 over 16, but it might be easier to do it this way. So the square root of 9 is going to give us 3, and the square root of 16 is going to give us 4. So the square root of 9/16 is equivalent to 3/4. And if we were to multiply that out, 3/4 times 3/4, which is 3/4 squared, we would get 9 over 16, so we do know that it works. Next thing we discuss is a perfect square. Give you a couple examples of these. The perfect square definition is a little confusing. The square of an integer is a perfect square. That means something raised to the second power. Or any number whose square root is an integer. Of course, you got to know what an integer is. So I'm going to tell you, integer does not contain any decimals or any fractions. So let's go ahead and pick a number. Let's say we pick 4. And then how do we square that number? We raise it to the second power. Now that doesn't mean 4 times 2. That means 4 times 4, which gives us 16. And 16 is considered a perfect square. Pick another number. Let's say 5. If we take the square root, if we square that, raise it to the second power, we get 25, and then 25 is also considered a perfect square. Any other number that has a perfect, or has an integer square root, let's say 100, and the square root of 100 is exactly 10. This is considered an integer because it has no decimals and no fractions. So 100 would be a perfect square also. Now we're going to estimate here the square root of 125, because 125 is not a perfect square. So what we need to start thinking of is, what is the next closest perfect square below and above 125? So I'm going to put 125 in the middle here. 125 square root. And then start multiplying numbers together. 9 times 9, 10 times 10. Well, 10 times 10 is 100. That's close, but I think I can get a little closer. 11 times 11 is 121. So 121 is the next closest perfect square below this. And then if I go to 12, 12 times 12 gives me 144. These two numbers are perfect squares. The square root of this is 11, and the square root of that one is 12. Now if we look at the 125, we can clearly see it's much closer to 121 than it is to 144. So we're going to say that the square root of 125 is approximately, and this is not equal, that's approximately equal to 11. It's actually 11 point something. but we'll just call it 11 because we're just estimating. Okay, here's the breakdown of real numbers. When you're first learning to count, we start with something like 1, 2, 3, and so forth. And when your parents are teaching you how to count, they point to things like your fingers or little objects around you. These are called natural numbers. And this pattern continues. Now, at some point, we teach you that there is actually another number over here to the left of 1, and it's called a 0. As soon as you add 0 to your natural numbers, that creates another group called whole numbers. But you'll notice in both cases, there's no decimals and there are no fractions. And then at some point, we learn that there's actually numbers even further to the left of 0, which are the opposites of these natural numbers, and we call those integers, like -1, -2, -3, and so on. And that creates another subgroup, or another group called integers. So natural numbers, whole numbers, and integers do not contain any decimals or any fractions. That's one of the easiest ways to identify them. Natural numbers, all natural numbers are considered whole numbers. All whole numbers and natural numbers are considered integers because these are subsets of their bigger sets. And then when you take anything outside of here that actually has a decimal or a fraction, even including negatives, let's say 3/4, 1/3, 2 1/4, -18.25, anything like this, and we refer to them as rational numbers. And one of the easiest ways to tell if you're looking at a rational number is to take whatever number you have here, divide it into its decimal form. In its decimal form, rational numbers will do one of two things. A rational number will either, when divided out, terminate, it'll stop going out in decimal form, or it will repeat. So you've got two types of rational numbers. You've got terminating, and you got repeating. Two types of rational numbers. Look at their decimal forms. That's the easiest way to know if it's actually a rational number. If it does not terminate or does not repeat, if it doesn't do either one of them, it's not called rational. It is then referred to as irrational. And examples of irrational numbers could be pi, or the square root of any number that is not a perfect square. These numbers here continue on and on and on and on forever without repeating. Last examples here are going to be compared in order. Sometimes you want to compare to see which numbers are larger than others, or put them in order. Maybe we give you a series of numbers and we want you to put them in order from least to greatest or greatest to least. One of the best ways to figure that out is to simply look at a number line. Let me give you two examples here. If I want to compare, by the way, we can use greater than, less than, greater than, equal to, or less than, equal to compare which one's bigger. And these always open towards the bigger values. And let's say I want to compare the number -5 to, let's say, -7. I want to know which one of these is the greater number. All I got to do is go identify them on my number line, or just envision the number line in your head. As you go to the left on the number line, the numbers get smaller and smaller and smaller, and as you go to the right, they get bigger and bigger and bigger. So as we see, here's the -5 and here's the -7. Anything to the right is bigger than the ones to the left. So the -5 is actually bigger than the -7. So we would open up this way. -5 is greater than -7. Suppose I wanted to know the square root of 25 versus 6.5. Well, 6.5 is pretty easy to find. It's right about here. And then the square root of 25 is 5 times 5, which is 25. So the square root of 25 is equal to 5, which is here. Which one is further to the right? The 6.5 is further to the right. Therefore, 6.5 is greater. So you can use this to compare, number line to compare, or if you're given a series of numbers, you can then imagine where they would all be on the number line. And then if you're going least to greatest, you start on the left, you work your way up, put them in that order, or greatest to least. If you're asked to do that, go backwards. And that's how we order and compare real numbers.